Okay, now that we've discussed the mean or the center of the sampling distribution, let's talk a little bit about the spread. Okay, number one, the goal is to have low variability. What does that mean? That means that when you take samples, find the sample mean, find the sample proportion, they're all about the same. They're not spread out all over the place. Okay, that's sort of our goal. And think about when we talk about spread and sampling variability, what are we really discussing? Well, we're really discussing the standard deviation. All right, so a couple things that we need to know before we start talking about the spread of sampling distributions. Number one, to get a trustworthy estimate of an unknown population parameter, okay, our goal is to use a statistic that's an unbiased estimator. Well, how are we going to know if it's an unbiased estimator? Okay, we'll get into that later. This ensures, remember, a biased estimator consistently overestimates or consistently underestimates a sample. And one of the ways to get an unbiased estimator is to make sure that you're taking simple random samples. And we'll talk about how your simple random samples, you can decrease the variability by taking larger samples, more samples, because it averages everything out. Unfortunately, if we do happen to get an unbiased estimator, it doesn't guarantee that the value of our statistic is going to be close to the actual parameter value. So we're going to take a look at the variability and see what is the best thing that we can do so that we don't get an unbiased estimator, so that we do get an unbiased estimator, not a biased estimator, okay? All right, so a couple different things. Number one, larger samples have a much better advantage over smaller samples. So they're much more likely to produce an estimate that's close to the true value of the parameter, which would make it an unbiased estimator. So here, all of these were samples of 100. So we did the count of 100 samples. So I took 100 samples, found the proportion of, let's just say, we were looking at, same thing with the red chips. Let's say we did samples of 100 and then found the proportion of red chips and put them in here. So in that sample of 100, these are each individual samples of 100. So a whole bunch of p-hats from the samples of 100. Okay, so this was 100 samples of size 100. This one was 100 samples of size 1000. Okay, so notice the variability or the spread here. So we're down from sample proportions from 0.22 to 0.52. That's a pretty big spread. But over here, when I did 100 samples of size 1000, notice the variability is, there's a few that are the 0.31 and 0.43, but most of them are much more precise at 0.34 to 0.40, and they're much more clustered about the same proportion. So the larger sample you have, the less variability you're going to have in your distribution. So the variability of a statistic is described by the spread of the sampling distribution. The spread is determined mainly by the size of the random sample. So larger samples give smaller spreads, and the reason for that is that you're sort of balancing out the, if we're talking about means, we're sort of balancing out, if there's an outlier at the low end or the high end, they balance each other out right in the middle. So the spread of the sampling distribution does not depend on the size of the population. Okay, so we don't really care how big the population is. The spread is not affected by the population. The spread is just affected by the size of the sample that you take, okay, and then find the population mean or proportion from that specific sample. And just remember, as long as the population is at least 10 times the sample size. So if each of these were samples of 1,000, we would need the population to be 10,000. If this was samples of 100, we need the population to be 1,000. So the population does not change what my sampling distribution looks like as long as the population is 10 times the sample size. Okay, so one important and surprising fact is that the variability of a statistic in repeated samples, like we said, does not depend on the size of the population. So that's the only thing we care about, is that the population is 10 times the sample size. So the question is, how do we distinguish between the mathematical theory versus the real world? That's when we use the 10% rule. Okay, so what exactly is that 10% rule? So the 10% rule is a numerical approximation that we're going to use very often in AP statistics, especially with sampling distributions, and then especially when we go and look onto inference. What is the 10% rule? The 10% rule is the population is at least 10 times the sample size. Okay, and remember in our previous sections that we talked about the 10% rule that allowed each individual with with binomial to be independent. So it allowed us to have independent because it doesn't change the probability when we do probability with replacement. So same thing applies here. We want the 10% rule, so the population's 10 times the sample size. If you want to take a look at the mathematical theory, go ahead and check out this course or this link right here. This will take you to the link that shows you why that theory works. Okay, so let's just talk about what exactly is bias, variability, shape, accuracy, precision, all these words. Okay, so let's think of a bullseye, and let's think of the true value of the population parameter as the bullseye of a target. Think of the sample statistic as an arrow fired at the target. So when we take a sample and we get the population mean or proportion, are we going to hit the population mean, or sorry, when we take a sample and get the sample mean or proportion, are we going to hit the true population mean or population proportion? So this is the ideal, okay? This is our target. This is the true mean or proportion. We got a whole bunch of samples, okay? And there's very low bias. There's basically no bias because we've hit the population mean or proportion. There's low variability, okay? It's not, my samples aren't sort of all over the place, okay? They're sort of all clustered in about the same spot. Okay, that's what our goal is. That's what we want it to be. So both bias and variability describe what happens when we take many shots at the target. Okay, so shooting your arrow, are you going to hit the target or are you going to be off? Okay, now notice it's no bias, like I said before. The mark is where it should be. It's low variability because all the dots are in the same spot. Now, if you have low variability, it doesn't necessarily mean that there's no bias. It doesn't mean that I hit the mark. It just means that all of my sample means or proportions that I got are all in about the same spot. Okay, so both bias and variability describe what happens when we take many shots at the target. What does bias mean? Bias means that our aim is off and we're consistently missing the bullseye in the same direction. So we're either overestimating the population mean or proportion or consistently underestimating the population proportion or mean. We're basically hitting the same spot every single solitary time. It's just not where we want it to be. It's like when you're bowling and you're consistently getting a gutter ball, you're really consistent. You have low variability. You're getting in the gutter every single time. It's just bias because it's completely off of the it's completely off of where you should be. Okay, so our sample values, if it's biased, do not center on the population value. And remember, you can either have an overestimate or an underestimate. So if we look at this example right here, this has high bias because it's very far away where it should be, but it has low variability because everything's in exactly the same spot. So we were really, really consistent with our overestimate or underestimate. Okay, so let's just take a minute and look at two other examples. So what happens if we miss the mark all over the place? Number one, we have low bias. Okay, well, I mean, we got, it's not no bias. It's not high bias. We're sort of around where we should be, but I don't know. We're not super close, but we have high variability. So I got dots all over the place here. They're not all in one spot. Okay, and for the second one, if you notice here, this is high bias because they're all really, really far away from where they should be. And there's high variability. They're not all clustered around the same spot, okay, in this wide range. They've missed the mark in the same wide range area. So there's high bias. We consistently overestimated here. And there's high variability because they're kind of all over the place. Low bias, we're kind of close to where we are, but it's still pretty high variability because it's all over the place. I haven't bias, remember, means consistently over or underestimate in the same spot. Here, we're all in the same spot, sort of overestimating. Here, we don't have bias because they're not all sort of clustered in one area. Okay, so the lesson about center and spread is clear. Given a choice of statistics to estimate an unknown parameter, your goal when we're using the statistics, your goal is to get one with no or low bias. Okay, and you'll never be able to completely eliminate bias just from random sampling. And you want minimum variability. So what does that mean? We want all of our sample means, sample proportions to be in the same area. Okay, so let's talk about accuracy and precision. This is often It's really easy to get confused. Okay, so accuracy means our estimate's in the right spot. So we've shot the arrow, we're accurate, we hit the bullseye every time. Precision means that our estimate has low variability, but it doesn't mean it's in the right spot. So accuracy, we're accurate, we hit the mark. Precision means that we're really precise in where we shoot, but it doesn't necessarily mean it's in the right spot. So precision is sort of like variability in the sense that if you have low variability but it's in the wrong spot, you still have a biased estimator. So precision means I'm really good at hitting the same wrong mark every single solitary time. Okay, so whenever you use these two terms, you just want to be careful with your wording. Here's an incorrect statement. Our estimate will be more accurate if we increase the sample size. Okay, so why is that not correct? It's not correct because it's not going to make our estimate in the right place. However, it will make it more precise. Okay, this means that we're going to have lower variability, or all the samples are going to be about the same value. So the larger the sample size, okay, the more precise it's going to be. So it's going to give us all numbers within that same area. It's not necessarily going to make it unbiased or more accurate. It's just going to make it more precise, all in the right spot. Okay, so here's a correct statement. Our estimate will be more precise if we increase the sample size. We're going to put them all in the same spot, but it doesn't necessarily mean we're hitting the correct spot. Okay, so let's just take a look at a couple of sampling distributions and see what it means. Which ones have low bias, low variability. Let's sort of apply those to a couple of different examples. All right, so when I do sampling distributions, that means I've taken sample mean, sample proportions, and put them in a distribution. The same statistic can have sampling distributions with different shapes depending upon the population distribution and the sample size, okay? Now, whenever you are doing inference, we want to make sure that you take a look at the shape of the sampling distribution before you do inference, because that's going to tell us whether or not we have a biased or unbiased estimator. Okay, so what this is sampling distributions for different statistics used to estimate the number of German tanks in World War II. Okay, so we've just used different statistics, so different type of samples, okay, to estimate the number of German tanks. So here we use the max and the min. Here we use the mean with 2 standard deviations. Here we did twice the mean, 2 median, partition. Okay, so it's just using different statistics in order to estimate the number of German tanks in World War II. The blue line right here represents the true number of tanks. Okay, now the first 4 were presented by groups of students. 1, 2, 3, 4. Okay, not this one. Okay, just these first 4. Okay, the partition method, which is this one down here, was recommended by the DC mathematicians. So let's just take a look at why this particular one was used as a recommendation by the DC mathematicians. So the graphs below show the approximate sampling distributions for different statistics when taking 250 samples of size 4 from a population mean of 342 tanks. Okay, so each of these have 250 samples, okay, of size 4. This line represents the true mean of the population. Okay, all right, so take a look at these. Which of the statistics appear to be biased estimators? Which are unbiased estimators? And explain why a biased estimator might be preferred over an unbiased estimator in this particular case. Okay, all right, so let's take a look at question A. So question A, if we're taking a look at our example here, the statistics B and E appear consistently too low. Sorry, let's just look at these. Okay, B and E. Okay, so here is B. Here is B and here is E. If we take a look at these, they're consistently too low, like way too low. That is the center, so their center of their sampling distributions would probably be like here and here, appears to be below the true mean of 342 tanks. Okay. Of the 3 unbiased statistics, A is the best, this is A right here, because it has the least variability. All right, so this has the least variability. Now remember what unbiased means. It means the mean of the sampling distribution is the same as the mean of the population. So the mean of this one is going to be pretty close to the 345. Okay, and on the last slide, or the last video, will take about 5 minutes and answer the questions B and C.